So hi everyone, this is going to be a review session and we'll be talking about graphs and graph algorithm design. Okay, so a quick agenda. We will start off by talking about Dijkstra's and A-star, then we'll go to MSTs, and then we'll go to graph algorithm design. And then I was too lazy to add the solutions to these slides, so if you guys want the solutions and you guys are watching the recording, you have to watch the whole recording. And a quick preface before we dive in. So this review session, unlike other review sessions, won't be actually like lecturing on content. It'll just be diving into problems, and most of the problems will be on the challenging side. So I expect if you're watching this, hopefully you've had a chance to review like lecture material, because this will just be on problems. Perfect. Okay, so let's start off by talking about Dijkstra's and A-star. So the first Dijkstra's problem we have here are two parts. The first part is what edges are in the shortest paths tree starting from L. And then the second part is decreasing which edge by 2 changes the shortest paths tree. And if there's multiple edges that work, determine all of them. Okay. So I'll give you all around, let's do around 6 minutes to try this part, and then I'll go over it. Okay, so we'll be going over the answers now. Hopefully you all had enough time. If anybody wants more time, you guys can just like speak up and then I can give a couple more minutes. So yeah, does anyone want more time before we dive in? Okay, so let's walk through the solution. Okay, so the first part, it asks for what edges are in the shortest paths tree starting from L. And so there's a couple ways we could approach this problem. One way is I could just like walk through the algorithm for Dijkstra's as shown in like Hug's lecture slides. My only problem with this, it takes a lot of time to keep track of like the distance to the edge to arrays. So it's helpful in an exam to walk through Dijkstra's more intuitively. And that's what I'll show you right now. So when I'm at L, all we do in Dijkstra's is we keep visiting the next closest vertex, right? That's all that Dijkstra's does. So when I'm at L, the next closest person is U. So we go to U. Then the next closest person, after going to U and learning information about the neighbors of U, is T. Then the next closest person is E, right? Then the next closest person, who is 6 away, is A, right? And then we see I and A best friends. We can easily go to I when we're already at A, right? Okay, so now let's see who's the next closest person to go to. Well, I don't really want to do the math, but you can kind of see here that the best way to get to M is like so, and the best way to get to S is like so, because this path is length 8 versus this path of length 9. Okay, so we quickly found the shortest paths tree. Does anyone have any questions? Okay, so part 2, decreasing which edge by 2 changes the shortest paths tree starting from L. Okay, there's something in the chat. Okay, so it says, assume the shortest paths tree was created by Dijkstra's from L. Okay, so what we're trying to do here is we're going to ask ourselves, at each edge in the graph, if I decrease its weight by 2, does the shortest paths tree change? Okay, so I think it starts off, let's look at all of the edges. Actually, I'm going to move to this solution slide that I created for myself. Okay, so let's start off by looking at each edge that's not in the SPT. Okay, so, and we're going to ask ourselves, if I decrease the value of this edge, can it potentially join the SPT, right? So let's look at more specifically all of these edges here, and we'll see Like if I decrease its value by 2, is it possible for it to join the SPT? That's like my initial intuition. So let's start off by looking at this edge LT. We see if it became 7, it doesn't really change anything. We're never going to use this edge, right? So nothing to do there. Let's move to UI. Okay, so this one actually will produce an interesting result. If I make this 4, now what we'll notice is that the best way to get to I is this blue path, right? Instead of taking this pink path we had before, or this now blue path that I shaded, we can see it's better to use this other path, right? So what we'll see is that the shortest path tree must change, but how exactly is it going to change, right? Well, what we're going to notice is that we don't need this edge anymore, right? Because we know we want this edge in here, because it's better to get to I like that. We realize that once we're at I and A are best friends, so it's easier to get to A via I, right? So we don't actually need this edge anymore, because it's faster to get to A via this path of cost 4 rather than this path of cost 5. Okay, so we'll say edges. And the first one is UI. Okay, so let's go back to how it was before. Okay, so we wanted to look at each edge not in the SPT so far. So let's look at IT. If I make this 5, we'll kind of notice it doesn't really do anything, right? So let's keep going. If I take this edge, I make it 2. Now notice I'd rather get to M via this path here, right? Okay, so let's add that edge here, IM. Okay, so then we'll look at this edge. If I make it 7, it doesn't really do anything. Finally, if I go here, actually there's 2 more to consider. But if I look at this edge ES, notice now that if I make this 3, the best way to get to S traverses this ES edge, right? Because it's a path of cost 7 versus the path of cost 8 that we had before. So we can add ES to our list of edges. Okay, finally, let's look at ET. If I make this 4, we'll see it doesn't really do anything because it's better to get to T via U. Okay, so it turns out that it's possible to actually decrease one of the edges in the SPT and still change the shortest paths tree. Okay, I think this is a little less intuitive. So the reasoning here is, suppose I decrease this edge by 2, right? We know that this edge, if it was in the shortest paths tree, it's going to stay in the shortest paths tree. But what's going to change then? Now, if I have some vertex that's kind of like on this path, we'll see that the total cost of this path has now gone down by 2, right? So it's possible now to get to S via path of cost 7, which is better than the path of cost 8 that we had before. So in this case, if I decrease EL, we are also changing the shortest paths tree by adding in this pink edge right here. Okay. Okay, so that's kind of cool. It turns out I can decrease an edge on the shortest paths tree, and it potentially can change the shortest paths tree, right? Okay, I'll take the questions at the end, so I'll quickly finish this. So the other one that we want to consider, I mean, there's a lot of edges in the shortest paths tree, but we can quickly see if I make this -1, it's not actually going to change anything. I'm still going to have the same shortest paths tree, okay? If I decrease this to 0, it's also not going to change anything. It's going to be the same as before. Okay, so it turns out the ones that do change are going to be if I decrease this to -2, now it's advantageous to go to M from here. Okay, because now this is cost 2, which is better than the cost 3 path we had before, right? So we can add that in there. AI. And yeah, I think that is all of the changes there are to be made. So does anyone have any questions on anything that has happened so far?
I have a quick question.
Yeah,
So
go
you
for it.
mentioned earlier, if it's already in the SPT, then it doesn't change like the shortest path. Then why was AI included? Was it because it's a negative number?
Yeah, really good point. So I'll kind of walk through that again. So the idea here is that if I decrease an edge that's in the shortest paths tree, in this case, I make AI -2, we're still going to include this edge because it's just gotten better. So what can change, however, is the idea that if I have somebody, in this case, let's look at M, that's farther down this path, you can kind of see here that now it's faster to get to M via I, right? Does that make sense? So now we would have this pink edge here if this became -2.
Okay, so then the path to M taking I would be 2 instead of 3
Yeah.
via a M's edge.
Wait, explain that once more.
So you're comparing the two routes. Like, yeah, it's easier to get through AIM instead of going directly from AM because of that negative number.
Yeah, exactly.
Thank you.
Yeah. Also, like in the chat, it says Dijkstras can't have negative edges. That's not necessarily true. Dijkstras may work with negative edges, but it may not. Okay? That's the idea here. If Dijkstras has negative edges, we aren't ensured that what we get is necessarily the shortest path. But it's still possible Dijkstra's works, right? And a really easy way to convince that to yourself is if I have a graph that's just like a line, like if everything's negative, I'm still finding the shortest path, right? So I can't say negative edges means Dijkstra's fails, right? It may make it fail. Anyways, that's a quick aside. So let's move on to the next part unless anyone else has more questions. What about MS? Okay, let's check MS quickly. I don't think MS would work. Okay, so let's move on to the next part, and then I'll try to answer the questions in the chat in the meantime. Okay, so for this next part, what we're doing here is we'll define the heuristic of a vertex V as the shortest distance between V and I. Okay, so for an example, if we look at T, the heuristic of T would be 3 because the shortest distance between T and I is 3, right? Okay, so the problem states that if I is the end vertex, which start vertex would visit the most vertices on one run of A star? Okay, so that is the problem, and then I'll give you all around, let's go, 5 minutes to tackle it. And then I'll take the questions in the chat now. So I think a good amount of people are finished, so let's try to go over this problem. So this problem is actually, I think, rather cool, and you'll explore something interesting about A star. So the idea here is that we have a heuristic that's really, really good, right? When we think about heuristics, a heuristic is usually an underestimate or some sort of guess at the shortest distance between one vertex and the end, right? So in this case, we kind of have something that I like to call a perfect heuristic, right? Where the heuristic of each vertex is the actual shortest distance. Okay. So this may seem like, hey, that's a cool observation. So I'm like, what does that really mean? Okay. So now what we're going to do is, let's just like suppose that I'm running, I don't know, Dijkstra's, or let's say, A star from S. Okay. And then we're going to see something cool arise because of this perfect heuristic. Okay. So let's notice that the priorities of vertices M has a priority of 3, T has a priority of 3, and E has a priority of 9. And where did I get these numbers from? It's because the shortest distance between M and I is 3. The shortest distance between T and I is also 3. And the shortest distance between E and I is 9 via this path. Okay? So when I'm at S and I'm asking myself, which vertex do I want to visit? What I do is I sum the edge weights plus the priorities of these three possibilities, okay? So if I want to go to T, T has a priority currently of 5 plus 3, which is 8, okay? M has a priority of 9 plus 3, which is 12. E has a priority of 5 plus 9, which is 14, okay? And what we'll notice, which is really cool, is that the value 8 for T is the cost of the shortest path to I via T. I'll say that again because I think it's really cool. The priority of T is the value of the shortest path from S to I via T, right? The priority of T is 8, and the shortest path to I via T is 8. And notice that this is also the shortest path from S to I, okay? So what we're going to do is we will visit T, and then at T, we'll say, who should we go to next? And what we'll notice is that since this heuristic is perfect, as I like to call it, we will only visit vertices on the shortest path between S and I, right? So we're never actually going to visit a vertex that's not on the shortest path because of this perfect heuristic idea, okay? So now what follows is we've realized that when I run A star and we have like this really, really good heuristic, I'm only going to look at vertices on the shortest path between the start vertex and the end. So the question boils down to which start vertex is the most number of vertices away from the end. So in order to figure that out, what we can do is create a shortest paths tree rooted at I. Okay? So let's quickly do that. If I create a shortest paths tree rooted at I, we will get the following shortest paths tree. And now what we'll notice is on the shortest paths tree, the vertex that's the farthest away from I is L, right? So what that means is the shortest path between L to I has the most number of vertices compared to any other vertex in the graph, right? And what we can say is that if I run A star starting from L, and I look at this shortest path, if I run A star, I'd have to go to U, T, A, and then I, which is more vertices than any other shortest path, okay? So the idea here is that L would visit the most number of vertices. Okay, so any questions on that one? Feel free to like speak out loud. Okay, so does anyone have any questions?
What's the motivation behind creating a SPT at I?
Yeah, it's a really good question. So the idea behind creating an SPT at I is we've noticed that when I have a really, really good heuristic and I run A star from any vertex, all I'm doing is just traversing the path, the vertices on that shortest path, right? So we want to figure out the shortest path between every vertex and I. And if we think about that in reverse, an easy way to figure out the shortest path between every vertex and I is finding the shortest path between I and every vertex, right? And to find the shortest path between I and every vertex, we just create a shortest paths tree rooted at I. Oh, I really like this raise hand feature. Okay. I'm gonna mess up your name. Shrestha?
No, you're fine.
Okay.
Yeah, so I noticed that the shortest path between L and I is like through like U and then going directly to I, right? Oh, actually, no, never mind.
Yeah, it's like deceptively this way because it's 2 + 3 is less than 6.
Okay, I
Yeah.
see. Okay, that makes sense. Thank you.
Any other questions? You can just speak out loud. You can raise your hand. Either way works.
So kind of a question. So we can think of like I being the end vertex. We can think of just finding the shortest path from I. Like in other words, like A star, which is like is kind of the reverse of Dijkstra or Dijkstra's.
A star just runs Dijkstra's. So A star is doing the same thing as Dijkstra's is doing.
Mm-hmm.
It just gives a different priority to every vertex. Okay, so
Right.
at a high level, when we run A star, we're solving a different objective. Okay, the objective of A star is to find the shortest path between a vertex A and a vertex B. In Dijkstra's, we're actually solving a different problem. In Dijkstra's, what we want to do is find the shortest path between a start vertex and every other vertex on the graph. Okay, in A star, we only care about going from one place to another place, like Google Maps, right? So the idea here is A star doesn't want to look at unnecessary vertices. In order to not look at unnecessary vertices, we add a heuristic so it kind of leads us to the shortest path, right? And when the heuristic is really, really good in this case, we only look at the shortest path, since there's no paths of like the same cost. Does that
I see.
make
So yeah. So the only reason we could make a shortest path here is because like rooted at I is because of the perfect heuristic.
Yeah, in essence.
Okay.
Yeah. Any other questions? Oh, somebody asked a good question. How would you solve this if the heuristic isn't, in quotations, perfect? So if the heuristic isn't perfect, I would just brute force run A star from every place. There's no slick solution. Okay. So let's move on to the next part. If you guys have other questions, feel free to voice them in the chat and I'll answer them. So now we're moving on to minimum spanning trees. Okay. The first problem is for prims, and there's 2 parts. Hopefully we can take a stab at both parts. So the first part is just like we have a graph, and what's the minimum and maximum number of times I could change the priority of a given vertex. And then part 2 is saying if I run prims from A, where this is A, we want to fill in the edges here such that the priority of C is changed the maximum number of times. And the second part is that we want to fill in these edges such that each vertex's priority is changed the minimum number of times. So yeah, I'll give you guys around, let's go 6 minutes. Okay, so let's quickly go over the solution. Okay, so for the first part, it asks, prims can change the priority of a vertex v in the fringe a maximum of blank times and a minimum of blank times. Okay, so it's really important here to understand why would we change the priority of a vertex when we run prims, right? So what's actually happening behind a change priority operation is we have found a better edge to a vertex, right? Whenever we change the priority of a vertex in the fringe, what we are saying is I have found a better edge to get to this vertex. So let me update its priority, right? So what we can see here is that it's possible that the first edge I look at is the best edge, and I never have to update after looking at that first edge. But on the other hand, it's possible that maybe the last edge I look at is the best edge, in which case I have to look at all of the edges coming out of one vertex before figuring out which one is the best, right? It's possible that every edge I look at makes me update the priority, okay? So the answers here are a minimum of 1 time and a maximum of, it's a little small here, the degree of v time, okay? So what is the degree of a vertex? It's the number of outgoing edges. So the degree of C is 4, since there's 4 edges outgoing C, okay? So that's just a little graph terminology. And the reason we have like a changed priority the first time like I look at a vertex is in prims, what we do is we set the priority of every vertex besides the start vertex to infinity when we start, right? That's what we learned in class. And then the first time I see a vertex, then I say, I'm going to make your priority not infinity, right? So we have to do it at least once because we have to change it from infinity to something when we see it. Okay, so that is for the answer for part 1. Does anyone have any questions? So v minus 1 is fair. Degree of v is like a bit better just because it's like specific to the vertex v. But it does rely on like you guys knowing about degree, which was like briefly covered in lecture. So yeah, if this is an exam question, maybe partial credit for doing v minus 1. Any other questions? Yeah, so just to recap, the degree of a vertex is the number of outgoing edges from that vertex. In other words, it's the number of neighbors a vertex has. So specific to v means that the degree of v is specific to v. On the other hand, if I say something like v minus 1, which was voiced in the chat, that's not specific to v, right? Yeah. Okay, so the idea here is that a common solution was, what if I just do v minus 1, right? And when I say this v, this is a big V. It's a number of vertices in the graph. Okay, so the reason this solution isn't specific to a little v here is because we're not leveraging the fact that I have information about v. More specifically, I know how many neighbors v has, right? So if I use big V here, it's not as good of an upper bound as the degree of v. Okay. Any other questions there? Yeah. Okay. So moving on to the next part. So the idea here is that we're going to run prims from A, and we want to fill in the missing edges such that the priority of C is changed the maximum number of times. Yeah. And then quickly going through it. So what we'll see is that when we run prims, in order to change the priority of C the maximum number of times, what we want is every time we go to one of these vertices, we have found a shorter path to C. More specifically, we have found a better edge to C. Okay, because in prims, we build an MST. So when we start prims, the MST so far is A, okay? And then what we're going to do is look at this edge. But we don't want to take this edge because we want to keep improving our edge to C. So let's make this really big. I don't know. Let's just do 9. Okay, but it can be like anything that's pretty big. So then what we're going to do is we're going to say, which vertex should we go to next? Let's go to G. G is the closest. So after going to G, we'll see that originally, let's say the priority of C starts off as infinity. Then we change it to 9. Now we're going to change it to 8 because of seeing this edge right here. Okay, then what we're going to do is like, let's go to the next closest person to the MST so far, which is B. So after going to B, what we will do is we will say we want this edge to be slightly better than the value 8. So what will happen is, let's just make this, I don't know, 7, right? Because then we're beating 8. And then finally, we want to go to F before we go to C so that we can consider this edge right here. So let's go to F. And then what we'll see is that like, we want this edge right here to once more update the priority of C. So we can make it 6 because that's better than 7. Right? Okay, so that's it for the first one. And there's many, many possible solutions here. The main insight is to notice that this edge should be bigger than this edge should be bigger than this edge, and this edge should be bigger than this edge, right? So that's like the main insight. Okay, so let's move on to part B before we take some questions. So part B says the priority of every vertex is changed the minimum number of times, okay? So what that is saying is every time I see a vertex, I have found the best edge to get to that vertex, okay? Because we have to change every vertice's priority at least once because it's initially set to infinity. So the minimum is 1. So we should just say, I see a vertex, I found the best edge. In order to make that happen, I'm actually going to keep a copy of this. Okay, so let's move on to B. Okay, so the idea here is when I see G, we want to have found the best edge to get to G. Okay, so same with B, C, and G. Okay, so let's just make this, I don't know. Let's say I make this 3. Okay, but it can be like any really small value. So after going to G, then what we'll notice is like we want this edge to be the best edge to get to F. So we never have to change it in the future. So let's make this other edge bigger than that, right? This is just any value that's bigger than 4 though. Okay, so then let's go to B. Okay, and then we want this edge to also be bigger than this edge to C, right? We want this first edge we saw to C to be the best one. Okay, so we can just make it like, I don't know, any big value. Let's just make it like 4 just to play a little close to the flames. Okay, and then what we'll do is we can make this edge right here. So you can kind of see this is like the MST. And what we've done is we've made it such that every time I see a vertex, I found the best edge. Okay. So yeah, that's basically all. Another like possible solution that's like a bit more extreme, just to like drive home the point, is you guys can just make these numbers really, really big and make this number, let's make this 3. Okay. But if you did choose to make this one smaller, let's say I made this one 0, we would have to have this edge be better than this edge, right? So in that case, like we would make this any number that's less than 4 if we go to C before G, okay? So just depending on like different possible solutions that you all may have entertained. Okay, any questions on this problem?
So why don't we consider 8? Is it because we would just want the smallest number for it would be the smallest connecting to C?
So you're saying like, why doesn't 8 update the priority of C?
Yeah.
Yeah, it's because like after seeing this number 3 here, we're like 3 is better than 8. So we don't want to like update the priority of C after seeing 8, right? We only update the priority or change the priority if we see a better edge. Okay? Does that make sense?
Mhm.
Nice. Any other question? Well, yeah. So somebody asked like, what's the degree? Oh, okay. So I think I could take the rest of the questions in the chat, unless anyone else has like a big question relating to some concept. Okay, so
Would it be possible
Yeah.
to instead of, I know we were trying to minimize the number of times we change the priority queue for C, but could you also do the same thing for two edge vertices at the same time, or would does it expand the problem a lot more?
I see. So is this minimizing or maximizing?
Either.
So in this case, we're actually not minimizing to C, we're minimizing every vertex. So I'd say your problem would be directed better to like, suppose we want to maximize the number of times I change the priority of C and F maybe. So you actually like, this is a good question. So I'll just like say it once more for everybody else. If I want to maximize the times I change the priority of both C and F, it's actually like not possible for both of them to achieve the maximum that we showed in this of the degree of V, okay? So the reason like both of them can't hit the maximum is that there's always going to be a vertex that's the last vertex we visit. Do you guys see that? So in this case, we know that either C or F must be visited last, right? They both can't be visited last. So if one of them isn't visited last, let's say that's F, we can see that F's priority can't get changed 2 times because we never saw this edge, right? So it's actually not possible to like have 2 vertices that are both changed the maximum number of times. I'm not sure if that answered the question though.
Makes sense.
Yeah. Okay, cool.
I have a question.
Actually,
Following up from
wait.
like another person's question.
Can we take the one person whose hand is raised and then we can get to you, Lucy?
Yeah, no problem.
Yeah, perfect. Go for it.
I was just wondering, so in some of our review sessions, they didn't really talk about prims having a distance to. It was only an edge to.
Yeah.
So like, where's the infinity coming from? Or just like infinity something like we should already know, like it's already just there.
So in prims, we do need to record the best distance to each vertex. So I'm not sure which review session wouldn't have included that. But in prims, we do need to keep track of like, what's the shortest distance from one vertex to the MST so far. And we usually keep track of that in like a distance to some sort of like distance map.
Okay, but you do, so even if it's not said like we should know that it always replaces infinity.
Yeah, so like in the Dijkstra's lecture, we do that. Off the top of my head, I'm not sure like if it's the case we do that in the Prim's lecture. That's like, yeah, one small nitpick. I'm fairly sure, but I'll check like in the meantime after this explanation. Yeah. Any other questions? I think Lucy, you had one question.
Yeah. So can I ask now?
Yeah, go for it.
Oh, okay. So if so say we're trying to make it like the minimum number of times. If we make AC 3, we would visit AG first, right?
Yeah.
So when we visit G, then we would check its distance to the neighbor. So in that case, then we would update C's distance to 8, which changes its priority. So if we want to only make it change once, then AC has to be smaller than 1.
Yeah, good question. So what's going to happen is that once we visit A, we set C's distance 2 to 3, right?
Okay.
Yeah. Does that make sense?
Yeah, all right, thanks.
Yeah, good question. Okay, so any other questions here?
Could you give a range of values that can be used for part A and B?
Yeah, yeah.
Giving us minimum bounds.
Okay, so for part A, all we need is the criteria that the edges are in. Oh no. Okay. Hello, am I still alive?
Yeah.
Yeah, we can hear you.
Oh. I have no idea what just happened, but like my computer just like turned black. Okay, sorry about that. Phew, that was scary. Okay, okay, good question. So I also like recommend if you guys are like feeling confident on this, like move on to the next part. I think we'll be going over Kruskal's like 1 and 2. But until then, so just kind of walking through like the range of values for A and B. For A, all we need to have happen is kind of looking here. We want edge AC to be greater than GC, to be greater than BC, to be greater than FC. Okay? So that's like for part A. For part B, let me just kind of do it in the same fashion than I did this other one. For part B, all that we need to have happen is, so there's two possibilities here. So possibility 1 is that we visit G first. Okay? So if we visit G first, that means that this AG edge must be less than the AC edge, right? So this requires that AC is greater than AG, okay? It also requires that, let me think about this. If I visit G first, it requires that GF must be less than CF, right? Because if I go to G first, we want this one to be the best, okay? And then in both cases, actually then the other possibility is if I visit C first, what we want to have happen is AC should be less than. Okay, somehow Siri was activated when I talked. No, Siri. Okay, and then we also want GF to be greater than CF. And then in both possibilities, we want BC to be big. Does that answer the question?
Yeah, thank you.
Was that a yes?
Yeah, right. Thank you.
Oh,
Can you hear me?
weird.
Hello?
Okay, I can't hear anything, Mike. Okay.
Yeah, people can hear me.
Oh, strange. It must be something with my audio then. You all can hear me though. Yes. Okay, perfect.
Yeah.
So, okay, let's just keep going then. Anyways, any more questions on this part? Okay, so let's move on to the next one. Phew. Okay, so I'll give you guys around 5 minutes for this part. And I'll be giving the answer to one, but I won't be walking into it in too much depth, just for the sake of time. Okay, perfect. So for the sake of time, I'm not going to spend too much time on this explanation, but the idea here is that if the edge weights are between 1 and 100, we can simply run radix sort, and that'll be in E time, right? So now what we can see is instead of the E log E we had before, now we're doing this in E time. So when we think about Kruskals, there's like the sorting time, right? Or if we use a priority queue, which is usually E log E, now it becomes E because of radix sort. And now what we'll see is that the operation that dominates in Kruskals is our weighted quick union, which is E log V, right? The weighted quick union is E log V because of us doing is connected operations for, in the worst case, E times, right? So now what we can see is that the runtime is going to be E log V. Okay, any quick questions there? That was a pretty quick explanation. Yeah, so like on an exam, you can assume no path compression unless we say otherwise. Any other questions? Oh, so the final answer is E log V. So the reason we can run radix sort here is that we can run radix sort when the things that we're sorting are composed of digits. Okay. So let me give like a slightly better explanation here. So the idea here is when we run Kruskals, it's composed of two parts, okay? It's composed of the work we do with the weighted quick union, and we use a weighted quick union to keep track of the connected sets, okay? And then we also either sort all of the edges or we put all of the edges in a priority queue because we need to visit all of these edges or look at all of them in increasing order, okay? Usually when we run Kruskals, what happens is this dominates the runtime because of this E log E term, right? The E log E can either come from sorting in E log E time or using a priority queue in E log E, okay? Now what's going to happen is with this restriction, we can sort using radix sort in E time. And then what we'll see is that the weighted quick union, which didn't used to dominate the runtime, now does because it's E log V. The question is, aren't log E? So usually in class, we say it's E log E. I do understand your point that like log E and log V are around the same, but okay, there's a lot of questions on this one. For weighted quick union, can we reduce for some optimal case? Okay, so I think the word optimal should be kind of replaced with like best case. Like when you say optimal, I don't imply that like the graph is like somehow perfect. It's just like what's the best runtime we can achieve now, assuming that we like use the optimal subroutines, in this case radix sort. So apologies if it was a tad confusing there. Yeah. And then usually when we refer to the runtime of Kruskals, it's usually E log E. So the E log V is an improvement, though. Oh. Okay, so that's interesting, Brian. In class, we usually say it's E log E. I am interested to see these review slides though. But okay, for the sake of time, I don't think this problem is like too important. So we can kind of talk about it at the end of the review session. So let's move on to part 2. Okay, so for part 2, what we're doing here is we want to run Kruskals, but we have no way of like figuring out if they're cycles or not. So what we're going to do is we're just going to keep inserting the next smallest edge and see if it creates an MST. Okay, so the idea here is we will keep inserting the next smallest edge, and then we're breaking ties alphabetically. So we do AM before AT. And then what we'll notice is that at this point in the algorithm, we see that we have IM and EL, and EL is alphabetically before IM, so we will choose EL. Then what we're going to see is that the last vertex we need connected is S. But when we run Kruskals, we're going to look at IM first. Okay, so it's actually going to fail. So will this produce a valid MST on the graph below? No. What will happen is that we will choose IM. Choosing IM is wrong. Okay, so the idea here is that which edge need to be changed, and if so, to what? Well, in this case, we want to encourage us to choose S before we choose this edge, right? So in order to add S to our MST, we would prefer to choose one of these two edges, right? So in order to use one of these two edges, there's two possibilities here, okay? So possibility one is that we can increase IM by 1. Possibility 2, and I'll talk through each of these after, is we can decrease ES by 1. Okay, so what we'll notice is if I make this 5, what will happen is that IM is now tied with ES, okay? Except ES comes earlier in the alphabet than IM, so we would take ES and we would find the MST, okay? The other idea is if I make this 4, we're producing the same idea where we will say ES and IM are tied, but ES comes earlier, let's take ES. But the reason it doesn't work for TS is that TS comes later in the alphabet than IM. So even if TS and IM had the same edge weight, we would choose IM in the tiebreak. Okay. Oh, yeah, this is another good let me think. Oh no, just kidding. It's a MST. Yeah. Okay, Daniel like shook me for a sec. Yeah, just kidding, that doesn't work. But anyways, any questions on this one? So yeah, these are the answers. Yeah, so quickly explaining this, if I decrease ES by 1 to make it 4, what will happen here is now we have a tie between IM and ES, right? And ES comes early in the alphabet, so we would choose this one first and we would have an MST. So the idea here is we just want to randomly insert V-1 edges and get an MST. And then the same logic applies for IM. For IM, if I make this 5, notice now that IM and ES are tied. So which one do we choose? We break ties alphabetically, and we choose ES because it's alphabetically first. Okay. Yeah, so when we compare edges, if I'm looking at the edge IM, I write it as IM because I comes before M in the alphabet. So it says here, edges are written in alphabetical order and as compared as such. So if I'm looking at the edge ES, I write it as ES, and I compare ES and IM, like how I compare two strings. Okay? And that's just the way that we like to like refer to edge comparisons. Yeah, so yeah, this is a good point. It should be either one of the below. Okay, yeah. Perfect. Okay, so for the sake of time, actually, okay, I really like this problem, so I'm going to try to squeeze it in. I just thought of it before this review session, so hopefully this works. But the idea here is now we're going to run Kruskals with limited cycle detection. Okay? So this is like a little confusing. So try to like pay attention now so we can understand what the problem is even asking. So we have this legend TA whose name is Sumer, and he pondered, what if we can only detect a maximum of k cycles during one run of Kruskals? Okay. So the idea here is if I have a 6-vertex graph, what is the minimum value of k for which we can ensure that Kruskals will always work? Okay. So if k is infinity, notice that I can detect an infinite number of cycles, so like Kruskals will always work, right? So we should probably find a value better than infinity. That's a bit smaller. So I'll give you guys, let's say, 4 minutes on this one. I think it's a rather fun question, so yeah, do give it a try. So the idea here is there's 2 possible solutions like the last one, okay? So let's start off with the modifying graph one. Okay, so say that we have some vertex u and a vertex v. And I'm trying to go from u to v. And let's say there's 2 possible paths I can take. I can either go via ABC, or I can go via some vertex d. Okay? So let's say that these are of the same weight. Okay? Actually, let's just make this even easier for ourselves. Let's just make this like direct. So in this case, notice that both paths are of the same weight. So like, which one do we choose? Well, we want to choose the path with, is it more or less edges? Less edges, okay? So we want to choose this path. So we want to have some way to like, yes, okay, this is a good idea. What if we add 1 to each edge? So good idea in the chat. So that's the idea. Now what we're going to have is this is 2, 2, 2, 2, 2. But, oh, this is, just kidding, I can do math. This is 5. Okay. But the problem with adding 1 to each edge is now we may actually not find the shortest path. Huh, why would that be the case? So notice that like adding 1, it may be a little too much to add. Right? It's possible that after adding 1, it changes the shortest path, but we want it to be a tiebreaker, okay? So the idea here is that if I add some constant, it may change the shortest path. So we want to add a really small number that's dependent on the number of edges in the graph, right? So that I can add a really small number and it's only used as a tiebreaker. So let's say I add a really small value, like, I don't know, in the chat somebody said 0.001. So this would work for this graph, but it's possible that like I have a really, really, really big graph, okay? So we can't just like use a constant. This number we add should be kind of dependent on the graph that we are given, right? So a cool idea for what we can add is we can add something like 1 over e, okay? Yeah, 1 over e, somebody said it in the chat. So where did we get 1 over e from? Okay, so the reason we got 1 over e is because we want to add some weight such that the new, like any path doesn't increase its total weight by more than 1, okay? Because in this graph, we're assuming there's integer edge weights, okay? So the idea is that if I have any path has at most e edges, right? Okay, So if I have a path that has at most e edges, if I add 1 over e, actually, let's just make this like a bit easier for ourselves. Let's do e squared, just so it's like a really, really small constant. But 1 over e would also work. It just makes this explanation a bit trickier. So if I have some path that has at most e edges, if I add 1 over e squared doesn't increase the total weight by more than 1. Do you guys see that? So now it just used as a tiebreaker. But yeah, so the idea is we just add 1 over e squared to each edge. Does anyone have any questions here? Yeah, so 1 over e would like 100% work. Yeah, so we can just do 1 over e squared, 1 over e, both would work. It's just like, when I make this claim, a path has at most e edges, that is true. But if I have a path with e edges, 1 over e times e increases the total weight by 1, right? But then there's only one path, which Ryan says, yes. So Ryan, you're completely correct. I just wanted the proof to be like a tad simpler, but I realized I kind of complicated people. But yeah, 1 over e would work as well. So we could say, if there's ever a case where there's like 2 paths, right? That's the only case where we would ever have to tie break. So if we have to tie break, it means one of the paths has at most e minus 1 edges, right? If there's like some sort of need to tie break. So that's why 1 over e would work. Okay. Any questions here? Yeah. So Henry, that's a really good question. So suppose that we have this situation. Okay, notice that this is the shortest path. But if I add 1 to all of the edges, what happens is that this path now becomes weight 8. This path becomes weight 6. So magically, this is now the new shortest path, right, Henry? So what we can kind of see is that if I add some constant, in this case, what we did is add 1 to each edge, we could potentially change the shortest path, which is not what we want. We want the offset to be used as a tiebreaker, not to change the shortest path entirely. Does that kind of make sense? So good question, Archit. If we have fractional edge weights, the ideas would still work. You would just need to find like the minimum difference between 2 edges in weight. And then make sure that the little constant you add times e is less than that small difference. Okay, so I realize we've gone a bit over, but the other possible solution to this involves a change in the pseudocode. I'll quickly show you guys just so you guys can see both solutions. The idea here is now, if we ever have 2 possible distances to get to a vertex, right? So let's say that if the distance to P is plus W is equal to the distance to Q, right? In this situation, notice that like the 2 distances are the same, right? So in this case, what we want to do is, and this should be an else if, by the way, not an if, that's my bad. It should be an else if. So the idea is that when we have a situation where 2 paths are the same weight, which one do we choose, right? So now we'll say like, if the number of edges to P, let's say like +1, is less than the number of edges to Q, then we use P. So the idea here is that in code, I can say if the distances are the same, we want to break ties. So what we're going to do is we're going to check if the number of edges on this path is less than the number of edges that we previously had to get to Q, then let's change how we're getting to Q. Right? So there's two possible ways. And this would imply that we would have some way of like storing number of edges. So maybe add in a map. Right? Okay. So that's the idea for the Dijkstra's modification way. Any questions there? Okay, so the +1 is because we see an edge from like P to Q. So like, that's why we need the +1. And then the other question is, would we always be able to find the second distance before we pop off the relative vertex? I'm a little confused by that one. Malika, do you want to explain a bit more?
Yeah, so in the case that, wait, could you go back to the drawing that you drew on the other side? Oh, you can't hear. Okay, wait.
Okay. Okay. Could we make both W's just W + 1? Okay, you want to expand, Ryan, on your idea?
Just on the two lines.
Dang it. Okay, my audio's not working. So you're gonna have to type in the chat. I apologize. I could restart my computer, but then I'd lose the recording. Oh, I see. So you're saying if I just make this W + 1. I'm pretty sure that's the same problem with doing the +1 to the graph from before, right? It's the same idea. It's like when we add 1 to all the edges, now it's like the same thing. So it's like it doesn't work. I mean, if you wanted to, you can add like 1 + e here. Yeah, that would work. Okay. So any other questions on this one? Did anyone think these problems are kind of fun? I thought they were pretty fun to do. But okay, tough crowd. All right, somewhat daunting. Yeah, they are rather challenging. But I think the takeaway here is that as you guys do like more of these problems, you guys learn like tools that you can apply to future problems. Like now you guys realize that I can add stuff to the edges, right? You guys can realize like I can like change the nodes. So I think what I'll do is I'll probably, okay, somebody asks, can I do a TV question? What is it? Oh, Daniel, can you explain what a TV question is? Oh, throwback. Sure. I am not a boomer, I promise. Okay, so I think what I'm going to do is I'm just going to like continue this review session just so I can record explanations for 3, 4, and 5. If you guys want to leave, you guys can leave. I won't give like any more time though to like try 3, 4, and 5, but just so other people have 3, 4, and 5, I'm going to walk through them right now. Okay? So if you guys want explanations for 3, 4, and 5, stay back. Otherwise, feel free to drop off. Okay, so let's go for 3, 4, and 5. Yeah, I could post the slides later. Yeah, but for everyone else who just would rather see this, I don't know, when the recording is published, yeah, thanks for coming and have a good rest of the day. Okay, so let's go over. Oh, I appreciate all of the support. Okay, so let's quickly go over 3, 4, and 5 just for the sake of time. Okay, so problem 3 states that we have to visit vertices in order of their subset. Okay, so the idea, I think this problem is like kind of confusing. So if I have some vertex A, and I'm trying to get to some, let's use U and V to be consistent. Let's say I'm trying to go from U to V, okay? And I have like a bunch of vertices, let's say like A, B, and C, D, E, and F, and then G, H, and I, okay? So the idea is that, let's say that orange is subset 1, blue is subset 2, and then purple is subset 3. So we want to explore all of the people. So if I go to any one of these people, then I have to go to a blue person, and then finally I have to go to a purple person, right? And then let's say I have to go to V, okay? So one possible path that would fulfill this requirement is like U to C, C to E, then E to I, and let's say like I to V, okay? So that's the idea. So a couple possible solutions. One possible solution is when I'm running Dijkstra's, let me quickly create another page just so I have a bit more room. Okay, so as usual, there's like a couple possible solutions. So let's modify Dijkstra's. Okay, so we have Dijkstra's algorithm here. So how we're going to modify it is if I'm ever at a vertex, when I say okay, looking at this step here, usually we can look at any other edge outgoing P, right? Now what we're going to do is only look at a subset of the edges. Relax a subset of the edges, right? Because if I'm at, let's say I'm at B right now, right? If I'm at B and I'm trying to visit somebody else, the only people I can visit are people in the next set, right? So all I can do, instead of relaxing all of the edges, I should only be considering these vertices here, right? So the idea is instead of relaxing all of the edges, we'll relax a subset of the edges. And this subset is going to be the next subset after P, okay? So that's the idea. We only want to look at vertices that are in the subset after B, okay? So that's the first idea. So The second idea is we're going to modify the graph slightly, okay? And what we're going to do is only include edges between adjacent subsets, and we're going to make these edges directed. Okay, so what does this mean? Let's say that I have some graph. Let's use the same one from above. Okay. What I can realize is I'm never going to use this edge between U and D, because we can kind of consider U in subset 0 and D in subset 2. So we can get rid of this edge, right? And then we're never going to go from A to B because they're both part of the same subset. We'll never go from A to C. We'll never go from C to B, right? And then what we can do is, since I'm at U, I can't go from A to U. I can only go from U to A. So let's make this directed in this direction, right? In a similar fashion, I can't go from C to U, but I can go from U to C, right? And then here, I can go from B to E. I can't go from E to B, and so on. So what we're doing is we're only including edges between adjacent subsets, and we're going to make these edges directed in this new graph that we're making. Okay? So yeah, those are the two ways. Since people are still here, does anyone have any questions? So someone asked, shouldn't there be a line from U to B? It's possible that there never was an edge from U to B to begin with, right? It's not the case that every vertex in one set can go to the other set, right? And then if we go to A, it turns out like, okay. So just to give a quick recap once more, if I have this drawing right here, okay? Let's just do it once more, the whole thing. So we want our final path to go from U to somebody in the first subset, then to somebody in the second subset, somebody in the third subset, and then to V. Right? This is what we desire in our final path. In order to make this happen, what we're going to do is we're going to say, I'm going to filter the edges in this graph so that if there was an edge from 1 to 3, I get rid of it, right? In other words, we're only going to keep edges that go from U to 1, 1 to 2, 2 to 3, or 3 to V, okay? And we're going to make all of these edges directed so that we can't go from A to U. Because if I have this undirected edge here, it's possible to go from A to U, but we can only go from U to A. So what we're going to do is remove all of the edges and only keep directed edges between adjacent subsets. Okay, so you can't go from one subset to the other, so we get rid of all of those. We keep these two. We can't go from U to D, but we can keep these ones here. Then what we'll see is we'll keep these two, and then we'll keep this one. Okay, so that's the idea. Okay, so somebody asked another question. For the solution that modifies Dijkstra's, if we only relax edges from other subsets, wouldn't the algorithm still might visit a node that is in the same subset that has the lowest priority? Ooh, yes, that's a really good question. So the question is that we may visit a node in the same subset that has lower priority. Okay, I think I see what Dana is going for. Okay, so let's try to remedy that case. Yeah, so Noah's fixes it if we reset the distance to array. Yeah, so I think that's a good fix. Okay, so the fix is like, so the problem, just to recap for everyone that's watching, is if we only relax edges from other subsets, wouldn't the algorithm might visit a node that is in the same subset that has the lowest priority, and then we can reset the distance to array after every subset change. Okay, so let's move on to the next one just for the sake of time. Okay, so this next one, I'm only going to give like one possible solution here. So it says we're trying to go from U to V, and we have to visit two designated vertices S and K. Okay, let's put them like this. So our path can either look like that, or it can kind of look like this, right? We're either going to go from U to K to S to V, or we'll go from U to S to K to V, right? These are the two possibilities. So what we can kind of see here is these are our two possibilities. So which one is better, right? That's what we're trying to figure out. So what we're going to do is we want the shortest path between, here's what we want. We want the shortest path between U to S, right? S to K, U to K, and then S to V and K to V, right? So these are like the 5 shortest paths we want so that this thing can hold here, okay? Okay, so in order to find like the shortest path between U and S, I can just run Dijkstra's from U, right? If I run Dijkstra's from U, I'll figure out the shortest path between U to S and U to K, right? Then what I can do is run Dijkstra's from V, and I'll find the shortest path between V to S and V to K. But then we'd also have to run Dijkstra's from S to find the shortest path between S and K, okay? So in this case, we've run Dijkstra's 3 times from U, V, and S, because we want to find the shortest path between U to S, S to K, U to K, S to V, and K to V, so that we can compare these two possibilities and see which one is better, okay? But there actually is like a slightly better way. If I only run Dijkstra's from S and K, then I get all the information I need. If I run Dijkstra's from S, I figure out the shortest distance from S to U, S to K, and S to V. In a similar fashion, if I run Dijkstra's from K, I figure out the shortest path from K to S, well, we already knew that, K to V, and K to U, right? So now we have all of this information, so we can just kind of compute these two paths, right? We either go from U to K, K to S, S to V, or U to S, S to K, K to V, and see which of these two is better. Okay, so that is the solution for 4. So just to kind of recap, we will output the minimum between the two paths here. And when I say path, what I'm saying when I have this little image here, or this visual, is u to k isn't going from like the edge u to k, it's the shortest path from u to k, okay? And in a similar fashion, k to s isn't just taking the edge from k to s, because k and s may not be connected. It's again the shortest path from k to s. And then s to v is again the shortest path from s to v, okay? Okay, so the question is, can you only run Dijkstra's from u to v as well? Because you can use the sk path in both cases, so its length cancels out. Oh, interesting. So the idea here is, yeah, so another way of doing it, let me quickly think. If I run it from u and v, okay. So that is correct. But I do think it's a bit more clear to just run it from S and K, because it gives us explicitly these paths. Okay. So okay. So we will also run Dijkstra's from S and K to get these. Okay. Any other questions on this one? Okay. So this last one, okay, we're almost there. Instead of starting from vertex u and ending at v, we will now make it such that we can start from any vertex in a subset of vertices and end at any vertex in a subset of vertices. Okay? So the idea here is I can start at any one of these vertices and I can end at any one of these vertices. Okay? And then we have like our graph here. So this solution is really clever, and I think it's really cool. What we're going to do is create a dummy node u and a dummy node v, and we're going to connect u to every vertex in the starting subset, and we're going to connect every of these purple vertices to v. And we're going to call this the ending subset. Okay? And now what we're going to do is simply run Dijkstra's from u to v. Okay? Okay, so that's it.